let us have an application of one-dimensional box problem to a molecular system. So, application of the 1D box model to pi electrons in a linear conjugated hydrocarbon This is called the free electron model. Free electron molecular orbital method. In short, FEMO, free electron molecular orbital. As an example, hexatriene molecule. This molecule one, two, three, four carbons. All right, this is the structural formula of the hexatriene molecule. It is a linear conjugated hydrocarbon, double bond, single bond, double bond, single bond. That's conjugation. All of you have taken organic chemistry, and therefore you should know such things better than I do. This model applies the particle in a box model to the pi electrons in the molecule. Now, as you know, if there is a double bond, one of the bonds is a sigma bond and the other is a pi bond. Each such dash indicates how many electrons? 2 electrons. So how many pi bonds are there in this molecule? 1, 2, 3 pi bonds. So the total number of pi electrons is how many? 6 pi electrons are present in this molecule. Now, the assumption is that the pi electrons in such a linear conjugated hydrocarbon are freely moving inside the molecule. This is such a simple model so that the actual geometrical structure is not important. We can assume the molecule to be a straight line, to have a straight line structure. Actually, it is the carbons which are on a straight line, like 1, 2, 3, 4, 5, 6 carbons. These are carbons. This model is invented by chemists, because chemists have certain ideas about the properties of pi electrons. And all chemists think that pi electrons, motion of pi electrons, are relatively free. Free means they can go to any part of the molecule freely. And then but also notice that free means we have to ignore the electronic repulsions. No interactions among the electrons is assumed. So a chemist thinks of pi electrons in such a molecule as a system of non-interacting electrons. And in this model, that assumption is used. So we have a one-dimensional box problem. Now we need to know the box size. The box size is usually taken as, let's say, 1.5 angstrom for an average carbon-carbon bond length. And then if the conjugated molecule has, say, 6 carbons in the chain, then there are 5 intervals, one less, in the chain. And the box length in this model is taken as the chain length. In our example, hexatriene example, 5 times 1.5 angstrom, which is 7.5 angstrom. You all know what angstrom unit is, right? 10 to the minus what? 10. 10 to the minus 10 meters. In this problem, there are 6 pi electrons. Let us indicate the ground level. This is EPS. This is 4 EPS. This is 9 EPS. Next one, 16 EPS. These are the allowed energy levels for a single electron in the particle in a box model. Now, the ground state for the total 6 electrons is indicated by this energy level diagram. What is the total energy? E ground for the total, for 6 pi electrons, 2 times EPS plus 4 times 2, or 8 EPS, plus 2 times 9, 18 EPS, and all the other levels are unoccupied in the ground level. So the sum, 10 plus 18, 28 EPS is the ground state for the total of 6 pi electrons using this model, 3 electron molecular orbital model. Okay, now, of course, experimentally, the ground state energy cannot be observed. Remember, energies are relative, and only energy differences can be observed. So we need to find another excited state. So let us consider the first excited state for the 6 electrons. Then, starting with the ground, it is clear that excitation from lower energy orbitals will produce more energy. So the easiest or the lowest energy requiring excitation is from the highest occupied molecular orbital. Notice that we are talking about the molecule. So our orbitals are what kind of orbitals? Molecular orbitals. Highest occupied molecular orbital. This is the lowest unoccupied. So the excitation, in this case, is from the HOMO to LUMO. That will produce the that will need the least amount of energy. So take one of the electrons and promote it to LUMO. What is the excited energy now? 2 times Fs plus 4 times 2, 8, plus 9 Fs, there is only one electron in this excited state, plus 16 Fs. This is 10, 19, 45. Or 35. 19, yes. 35 Fs is the total energy. What is the energy difference? Energy of excited state minus energy of ground state for the total pi electrons. This gives us 7 Fs. All right? We could have obtained this delta E directly by looking at these two numbers. LUMO energy minus HOMO energy, it will give the same result. Why? Because it's just a sum. These terms, 2 epsilon, 8 epsilon, are the same in both cases. 7 Fs. Now, that delta E, this excitation energy, can be observed experimentally by an absorption experiment. Okay? So, for this case, let us calculate the excitation energy required, which is 7 Fs, but we will obtain 7 times Fs in actual numbers. Definition of Fs is h squared over 8 times mass. Here, what kind of particle do we have? Electron. So this is the mass of electron, 1 electron. And the box length. A is this. Mass of electron, we look up from a table of constants. This is 9.1. 109 times 10 to the minus 31 kilogram. H 6.626 times 10 to the minus 34. We are using SI units in this calculation. Then use your calculator, plug in the numbers, and you will find delta E to be 7.5 times 10 to the minus 19 joule. You may rewrite the same energy using a different unit, such as electron volt, EV. And in EV, it is 4.68 electron volt. How do I obtain, what is the conversion factor from here to here, or from this one to that one? You see here EV. This means E times volt. E is the magnitude of electric charge on electron. What is it? 1.6 times 10 to the minus 19 coulomb. Coulomb times volt gives joule. So if you take this number and multiply with 1.6 times 10 to the minus 19, you will obtain this. Or from here, to obtain this one, you take this number and divide it by charge on the electron. without the sign, of course, the magnitude. Now, this is the excitation energy. If we ask, what is the wavelength of photon which is needed to cause this excitation, then the photon must have the energy which is equal to this value. In this calculation, photon energy equals delta E. You should use SI units, all right? If the energy could be given to you or in terms of some other unit, say electron volt, but in order not to make silly mistakes, convert everything to SI, meters, kilogram, second units, and then proceed. Everything is automatic then. We may write this because we are asking what is lambda of photon. We may rewrite this expression like this, or lambda is h times c over 7.5 times 10 to the minus 19. Of course, here c must be in meter per second, not centimeter per second, but meter per second. So plug in h, you will obtain 2.65 times 10 to the minus 7 meters, which is the same as 265 nanometers. So this is what we expect for the wavelength of the light, which would cause this transition in our hexatriene molecule. This is a very, very simple model, isn't it? Extremely simple. But this model was used during the 1950s in paint industry. Because colors of materials arise from emissions from the substance, and if it looks red to your eyes, that means some red light is emitted from the substance. But the wavelength of the light from the substance depends on delta E of the material itself. And in this paint industry during 1950s, some people used this model to predict what kind of molecule should I design so that it will have a certain color. And it was a very, very useful guide. So sometimes, regardless of the simplicity of the model, it could be quite useful. All right, so this was our example. Let us erase this. And now we will go to another topic, rotational motion. So we have rotational motion and the rigid rotor. This means we are starting with lecture notes 4. Everything I'm going to discuss are contained in these notes. Now here, the type of motion is described in this manner. The motion is in 3 dimensions. We have a particle with mass m. This particle has a certain distance to the origin. So this is r, but the type of motion we are considering has a constraint, has a restriction. What is that? The distance of the particle is not changing. So r has a constant value, same value during the motion. Now, if you use Cartesian type variables, how would you calculate the distance from the origin to the particle? You would write x squared plus y squared plus z squared. These are the Cartesian variables of this particle with mass m. But this says the distance is the same during motion. So this has to be equal to. All right. Now, from this up to now, from the things we discussed, what do we infer about degrees of freedom for such a particle? The motion is in 3 dimensions. However, there is a constraint. Now, any particle in 3 dimensions will have 3 variables if we use Cartesian type, x, y, z. But are these variables independent if there is such a constraint? How do we know how many independent variables there are? We start with total number of variables, in this case x, y, z. And then we ask, are there any constraints among the variables? Which means, are there any relationships among the variables? Then, for each relationship, equality among the variables, we subtract 1 from the total number. Here, we start with 3 variables. Are they independent? There is a relationship among the 3 variables. We are assuming this R0 is given. It is given to us. It is known. So there is one relation among x, y, z. That means the truly independent variables are how many? 3 minus 1, which is 2. So this motion with this restriction, there are only 2 degrees of freedom. Now, selection of the type of variables is important here. If we use x, y, z as our variables, then at each step in our calculation, we have to remember this constraint, which means if you select x and y independently, you have to make sure you have to calculate z from this relationship, isn't it? So we look for some other type of variables to see if the problem becomes simpler. Well, the first type thing that comes to our mind is spherical polar variables, in which One of the variables is r, the other is theta, and the third one is phi. Now, using this type of spherical type polar variables, it is easy because r can be fixed as r0, and then this choice for r has no effect on selection of theta or phi. So theta and phi are completely independent. Range of theta is from 0 to pi. Range of phi, this one 0 to pi. This one 0 to 2 pi. So if we show them on the diagram, this is the angle theta. And then on the xy plane, measured from the x-axis, is the angle phi. So the actual motion here this is a sphere with radius r0. The particle is somewhere on the surface of this fictitious sphere, of course. It's not a real sphere, but it's a fictitious sphere. But we can describe it more easily using this sphere concept. This particle has such a motion that it must be always on the surface. It must always touch the surface of this sphere with radius r0. So the general motion of such a particle is just rotation, isn't it? Rotation on the surface of this sphere. One important point that you may see from this diagram is that look at this line. The magnitude is, of course, r0. Let us say origin there. What is the direction of the linear momentum of this mass? Think of it classically. Because it has to be always on the surface of the sphere, the linear momentum of the mass must have such a direction. What is the conclusion of this direction of linear momentum to the direction of this line? The graph is telling you, say this is the radius vector. As the particle moves, the radius vector also going to move, all right? But the direction of the linear momentum must always be tangent to the surface of the sphere. That means the angle between linear momentum and the position vector is 90 degrees, isn't it? So this is a right angle. During all of the motion, that right angle does not change. It is because the distance of the particle to the origin can never change by assumption. Now, whenever rotational motion is discussed, the concept of angular momentum is very useful. So let us discuss angular momentum. Classically, angular momentum is a vector. Capital L is a standard symbol used to denote angular momentum. You may see it in many textbooks about quantum chemistry. If there is a symbol L, most probably they are talking about angular momentum. Now, we have discussed the angular momentum a couple of lectures ago, but I'm repeating once again. The definition is, this is the position vector, and this is the linear momentum vector of the particle, and this cross product gives the definition of angular momentum. It is also useful to remember some basic facts about vectors. Those two vectors on the right side, r vector and p vector, they define a plane. Because if you have two directions, one direction like that, another direction like that, then those two directions will define a plane. Property of cross product is the result is another vector, as the notation indicates. There is an arrow. The resultant vector is perpendicular to the plane formed by R and P. This is true for any vector, like A cross B. Direction of C is perpendicular to the plane formed by vectors A and B. A direction, B direction, there is a plane. C is perpendicular. Okay? So, for example, if that particle is further constricted, instead of being on the sphere, if it were restricted to be on the plane. Okay? So then, in that case, it would describe a circle. And the angular momentum for such a particle would be perpendicular to the circle. And the only non-zero component would be z component for the angular momentum, because both vectors are on the same plane. It's a property of cross product that magnitude of this vector can be obtained from information about R and P. It is R times P times sine of angle between them. R is the magnitude of the position vector. P is the magnitude of linear momentum. Alpha is the angle between position vector and linear momentum. For example, in this problem, because the angle is 90 degrees, you would put 90 degrees here, and sine 90 is 1, isn't it? But this is so let us proceed with that. Alpha is pi over 2, or 90 degrees. And then in our problem here, so that magnitude of L is simply R times P. Or magnitude of linear momentum can be obtained from magnitude of angular momentum divided by magnitude of position vector. Remember, in our problem, this r has a constant value. It is equal to r0, capital R0. Now we can write the kinetic energy, classical kinetic energy. Up to now we use this expression, isn't it? P squared over 2m. P is linear momentum, magnitude of linear momentum. But in this problem, because of this relation, we can rewrite kinetic energy using angular momentum. So we have L squared over R squared. There is a 2m. Now, in our problem, this rigid rotor problem, R has a fixed value, R0. R equals R0. So this is given. Mass of the particle is also given, which means m times this factor becomes m times R0 square. This is a constant, isn't it? Mass is constant, R0 is constant. Both of them are given to us. It's a characteristic property. This quantity is called moment of inertia. So that we may write this expression as L squared over 2I. Note the similarity between the expression for kinetic energy using linear momentum. This is for linear motion. The kinetic energy for rotational motion is written like this. For rotational motion, very similar. Square of momentum here and also here. But this, in the upper expression, it is square of the linear momentum because the motion is linear along a straight line. All right? In the lower expression, this momentum is angular momentum because the motion is rotational motion. 2 is the same in both of them. Instead of mass for linear motion, in the case of rotational motion, it is replaced with moment of inertia. Otherwise, very, very similar, isn't it? Now, this is the classical, these are classical expressions. But before writing down the quantum mechanical expression, let us ask the following. L is the magnitude of angular momentum, okay? Now we ask, what are the possible values classically for the magnitude of, in other words, which numbers are classically expected for the magnitude of angular momentum? The answer can be obtained by looking at this expression, because if you know kinetic energy, you can find out what is magnitude of L, isn't it? So I ask, what is the minimum value possible classically for the kinetic energy. What was it? We had discussed this several times. 0 is the minimum value. Then, is there any upper limit for kinetic energy? No. So, are the values from 0 to infinity, are they changing continuously, or are the numbers jumping from one value to another value to another? Which one? Continuous changing. This is classical situation. If kinetic energy is changing continuously from 0 to infinity, that means magnitude of L is also changing from 0 to infinity continuously. We are emphasizing such points because later we are going to compare quantum results. Are we going to have a similar pattern, or are there going to be some differences? Now, quantum results, quantum mechanical, take this expression and make the quantum replacement. The only quantity we are replacing in quantum mechanics is components of linear momentum. Only this P is going to change in the quantum expression. All right? R is the same. So we will have R cross product P. But now this is operator. PQ is minus I times H bar times partial derivative with respect to qth variable. Here, Q is either X or Y or Z. In writing, in converting angular momentum to quantum mechanical expression, it is necessary that you stay with Cartesian type variables, which means linear momentum over there will have P. It has three components, Px, Py, and Pz. These are linear momentum components. Px is this expression with Q equals X. Similarly for Py, similarly for Pz. Now, on the right side here, R is the usual multiplicative quantity. But P is an operator here because of the derivative here. That means the overall, this is an operator. That operator is angular momentum operator, and it is a vector. So you see, it is exactly similar to this expression, but what is the difference? In the classical expression, components of angular momentum, X component, Y component, Z component, they are scalars. Because components of position vector and also linear momentum vector, those components are also scalars. However, in the case of quantum mechanical expression, because components of P are minus I times H bar times partial derivatives, they become operators. So, and what is the Hamiltonian? Operator. Kinetic energy, kinetic plus potential energy. In this problem, there are no forces affecting this rotation on the surface of the sphere, which means potential energy has a constant value, and we take the constant value as 0. as before. So that means Hamiltonian is only kinetic energy, and this becomes, and the expression this expression in which you replace L here with operator L square. And the Schrödinger equation H psi equals E psi with this H. Now we need to make the expressions more explicit. So what we do is we write the x component, y component, z component using the vector product. Because in our expression, to write down explicitly square of the angular momentum operator, we need to know expressions for x component, y component, and z component, and then add up. Now, we start from the definition. X component is y times pz minus z times py. Y component of the operator is z times px minus x times pz. Finally, z component of the operator is x times py minus y times px. These are more explicit expressions. Next, for the operators pz, py, and px, you replace these partial derivatives. Then the expression is in terms of x, y, z variables, Cartesian type variables. Okay? On the other hand, what did we say at the beginning of this topic? That using x, y, z variables is not convenient. What is the reason? Because in every step of the calculation, there is a constraint. X squared plus y squared plus z squared must be equal to a constant. To avoid that, we have selected spherical polar variables. Then we can separate one of the variables r and set it equal to r0. Then we just have the angle variables. But to be able to do that, we need to start with these expressions in terms of x, y, z, and then convert it into r, theta, phi variables. How is this done? This is done using rules of calculus. So what you do is, for any function, you start with this expand this, then you will see the partial derivatives explicitly. Then use the relationship between x, y, z variables and r, theta, phi variables. And then change the partial derivatives from x, y, z into r, theta, phi. This has to be done using rules of calculus. Change of variables in expressions containing derivatives. Here are all derivatives are first derivative, because p, as you see over there, is first derivative with respect to x or y or z. So it can be easily done. Of course, our topic, our course is not math. It's not calculus course. So I will just give the final result, which are indicated in the lecture notes. The final result in terms of r theta phi after converting is, for the x component, it is I times h bar sine of angle phi times partial derivative with respect to theta plus cotangent theta times cosine phi times partial derivative with respect to phi. The final expression for y component is minus I times h bar. Does everybody remember the meaning of h bar? What was it? What was the definition? Planck's constant divided by 2 pi. Don't forget that. The bar is important because numbers will change. This is cosine phi minus cotangent theta sine phi times partial derivative with respect to phi. The simplest expression is for the z component. It is minus I times h bar times partial derivative with respect to phi only. This is the simplest expression for the z component. Please note that this expression for the z component looks exactly similar to this one. But the variable is phi variable, polar variable, not Cartesian. This expression, all variables must be Cartesian. This is, you may say, coincidence. It just happened. But the z component comes out in a exactly similar form as the Cartesian type variables. In these conversions, we started with x, y, z variables and replaced them with r theta phi variables. In making this conversion from Cartesian variables into polar variables. Notice the right side. Do you see this symbol anywhere? No? But when we started for this conversion, we did not omit the r. R was included. R, theta, phi, 3 variables. 3 variables at the beginning, 3 variables at the end. But as a result of the simplifications, cancellations, r disappeared. So that you see only angle variables here, theta and phi. Also here, also here. So these are, there are no assumptions here about r equals a constant. Okay, we have to stop.